Greetings and welcome to Distiller. In the previous two classes, we have discussed about real gas equations of state, right? Real gas equations of state. So in that, we discussed about the van der Waals equation. The van der Waals equation, which stated P plus A by V square times V minus B is equal to RT, where A by V square is known as the pressure correction factor and B is known as the volume correction factor. All right. Then we discussed about the very general equation of state for a real gas, which is PV is equal to ZRT. All right. Over here, Z is the compressibility factor. So we discussed that Z in certain cases, for an ideal gas, it is 1. Z is 1 for an ideal gas. For real gases, it's either greater than 1. In that case, we say it's positive deviation from ideality. And in some cases, it is lesser than 1, where we say it is negative deviation from ideality. And also in certain cases, it is negative, it is lesser than 1 for certain pressure, a certain pressure range, and then it goes ahead and it goes greater than 1 after certain pressure. At lower pressures, it is lesser than 1. At higher pressure, it is greater than 1. All right. And similarly, for certain temperatures as well, for certain cases, Z is less than 1 for certain temperatures and Z is greater than 1 for certain other temperatures. All right. So certain high temperatures. So in that case, if Z transforms from less than 1 to greater than 1, then at the point where this transformation takes place, that temperature is known as Boyle's temperature. All right, that temperature is known as Boyle's temperature. All right, so the temperature at which Z transforms from Z less than 1 to Z greater than 1, in that temperature is known as Boyle's temperature. All right, keep this in mind. Okay, so this was about the compressibility factor. And then we discussed the virial equation of state, which was mentioned in terms of parts of volume or pressure. So we had PV by RT, which is Z is equal to 1 plus B by V plus C by V square and so on, which can also be written as 1 plus B dash P plus C dash P square plus so on. All right. So over here, B and B dash are known as second coefficients, second van der Waals coefficients. C and C dash are known as third van der Waals coefficients, and so on. So the second van der Waals coefficients, they basically tell you the molecular interactions. They account for the molecular interactions between two molecules. The third van der Waals coefficients, they account for molecular interactions between 3 molecules, and so on. All right. So virial equation is most applicable for high volumes and low and moderate pressures, so that the equation, it converges easily. All right. So this was about the virial equation. And then we discussed the principles of corresponding states, in which we had to calculate the reduced temperature, which is T by critical temperature, and the reduced pressure, which is P by critical pressure. And we discussed that if two gases are at same reduced temperature and same reduced pressure, then in that case, both of them have the same compressibility factor, Z, based on which we discussed about the generalized compressibility charts, and we solved problems based on this. So this was all about the equations of states. All right. There are many more equations of states, but these two are mainly very important and quite a lot used. All right. So we'll start today's lecture with this problem. Heat capacity of air can be approximately expressed as Cp is equal to 26.693 plus 7.365 into 10 to the power minus 3T, where Cp is in joule per mole Kelvin, or we can also call it as kilojoule per kilomole Kelvin, one and the same thing, and T is in Kelvin. The heat given off by 1 mole of air when it is cooled at 1 atmospheric pressure from 500 degrees Celsius to minus 100 degrees Celsius. So since it is heat given off, so definitely heat is going to be negative. All right. So we only have to calculate the mod of Q, which is actually at constant pressure, since we are dealing with constant pressure situations. Therefore, the mod of Q, since at constant pressure, mod of Q is equal to mod of delta H or mod of dH, which is nothing but integral n Cp dt from lower temperature to higher temperature. So over here, it's minus 100 degrees Celsius, which is 173 Kelvin, to uh, to 500 degrees Celsius, which is 773 Kelvin. So we are going to integrate this equation. So that is 26.673 plus 693 plus 7.365 into 10 to the power minus 3. All right, so we have to integrate this entire thing from 173 to 773. So when we integrate and find the answer, we'll get it as 18.11 kilojoules. All right, 18.11 kilojoules. So on the basis of that, this becomes our answer. All right, keep this in mind that n over here, since over here Cp is in kilojoule per kilomole Kelvin, and they have given 1 mole, right? 1 mole, and n you need to take in kilomole, right? So n is going to be 1 into 10 to the power minus 3 kilomole. Keep this in mind. All right, n you are going to take as 1 into 10 to the power minus 3 kilomoles. So multiply this entire thing by 10 to the power minus 3 and then solve the integration. So you'll get 18.11 kilojoules. Hence, C part is the correct answer. All right. Then we move on to a few important thermodynamic equations. They are used somewhere or the other. All right. The first equation is Antoinne equation. The Antoinne equation relates vapor pressure. We have discussed about vapor pressure, what vapor pressure means, and temperature. All right. So basically, you must have seen through steam tables or other property tables when we had used them. So at different temperatures, we had different saturation pressures, right? We had different saturation pressure. So in that case, the Antoinne equation is used to relate vapor pressure and temperature. All right, vapor pressure and temperature. Okay, so A, B, and C over here are known as Antoinne constants. All right, A, B, and C are known as the Antoinne constants. So this equation is very extensively used in thermodynamics in order to relate vapor pressure and temperature. All right, so vapor pressure can be found out at different temperatures using this equation. All right, this problem came, it was actually not directly given that it's an Antoinne equation, but it's somewhat the same thing, the Antoinne equation. So basically over here, if we take C equals to 0, then this equation simplifies to A minus B by T. So over here, they had given ln P saturation. All right. So this is one of the forms of Antoinne equations. All right. So over here, you have vapor pressure in atm and temperature in Kelvin. So this is how vapor pressure is given. So we have to approximate the vapor pressure of water at 50 degrees Celsius. All right, we have to find the approximate value of vapor pressure at 50 degrees Celsius, where the constant A is not known. All right, constant A is not known. So now over here, we are going to use the rule that whenever we are at the boiling point, whenever the temperature is equal to the boiling point, then in that case, the pressure, the saturation pressure is equal to 180. All right. When temperature is equal to the boiling point, then saturation pressure is equal to 180. All right. So for water, boiling point at 1 atm, boiling point temperature at 1 atm is equal to 100 degrees Celsius, which is 373 Kelvin. Okay. So we have this data All right. And then we have to calculate vapor pressure at 50 degrees Celsius, which is 323 Kelvin. All right. So we have to find the vapor pressure at this particular temperature. We have to find the vapor pressure at this temperature. All right. So now we are going to use the equation that is given. So ln P saturation, that is 1, is equal to A minus 5000 by 373. And the second equation we are going to form here, ln P saturation is equal to A minus 5000 by 323. So when we subtract equation 1 from equation 2, we'll get ln P saturation by 1, which is ln P saturation, is equal to A gets cancelled. All right. So we'll finally get 5000 times 1 by 373 minus 1 by 323. We have subtracted 1 from 2. All right. We have subtracted equation 1 from 2. So it becomes 5000 by 373 minus 5000 by 323. All right. So this we have to find out. So from here, saturation pressure is going to be e to the power 5000 into 1 by 373 minus 1 by 323. All right. This is going to be the saturation pressure. So the answer, it comes out to be 0.125 atm. All right. So approximately 0.13 atm. So this is the correct option. All right. Then we move on to the next very important equation, Clapeyron equation. So basically what happens when two phases coexist? For example, when we talked about vapor liquid equilibrium. All right. When we talk about vapor liquid equilibrium, or let's consider the diagram which we considered a few lectures ago. We had the PV diagram and we had at a particular temperature. This was the diagram. And at different temperatures, when we consider the same diagram where this is the point of saturation, saturated liquid, and this is saturated vapor. And at different temperatures, when we consider the same diagram, so we can make a locus of saturate points of saturation. That locus actually has its peak at the critical point, right? That is what we discussed, right? So now, if we consider these as the equilibrium pressures, all right, this as the equilibrium pressure and this as the temperature, all right. So and this is basically the change in volume, right? This is delta V, all right. Gaseous volume minus liquid volume, right? And similarly, there is going to be an enthalpy of vaporization over here, which is going to be delta H, right? Delta H. So now the the Clapeyron equation, it relates these equations in this manner. dP by dt is equal to delta H by T delta V, where T is the temperature, all right? T is the temperature, the equilibrium temperature. Delta H is the enthalpy of vaporization at that particular temperature. Delta V is the change in volume, all right? The change in volume during vaporization. That is the gaseous volume minus liquid volume. All right. So this is what we have. So based on that, we can get dP by dt, the slope. This is also known as slope for pressure versus temperature diagram. This gives you the dependence of pressure on temperature, the dependence of equilibrium pressure on temperature. All right. So this is the Clausius-Clapeyron equation. This is used in a variety of applications for thermodynamics. All right. Then, as a special case of the Clapeyron equation, we have the Clausius-Clapeyron equation. So what happens when we come from the Clapeyron equation to the Clausius-Clapeyron equation? We assume that the temperature is very, very less than the critical temperature. All right. If it is so, then you can clearly say as the temperature is lesser, as it is going, away from the critical point, this distance between the saturated liquid and saturated vapor, it keeps on increasing, right? So if T is very, very lesser than Tc, then delta V would be too much, right? That means the volume of saturated vapor minus volume of saturated liquid is going to be very, very much. All right, it's going to be very high. So in that case, this liquid is going to be so less in comparison to the vapor volume that we can actually neglect this. We can neglect this. So we can simply substitute delta V is equal to gaseous volume. All right, this is one assumption that we take. All right, this is one assumption that we take, that temperature is very, very lesser than critical point, critical temperature. Therefore, volume is going to be very, the gaseous volume is going to be much more than the liquid volume. So it can be neglected. Okay. And one more assumption that we take is that delta H, enthalpy of vaporization, it is usually considered constant. All right. It is considered constant, that is independent of pressure. All right. Independent of pressure and temperature. All right, both. Independent of pressure and temperature, usually independent of temperature. All right, that is one thing. And one more thing that we have over here, that the vapor, it follows the ideal gas law. All right, the vapor, it follows the ideal gas law. These three assumptions we take. First, that the liquid volume is negligible in comparison to the vapor volume. Second, enthalpy of vaporization is constant. And third, that the vapor acts like an ideal gas and it works according to the ideal gas law. All right. So when we come to the Clausius, Clapyeron equation. So from the Clapyeron equation, in place of delta V, we will simply write down Vg. All right. And then we are going to use the ideal gas equation. PVg is equal to RT. Hence, Vg is equal to RT by P. All right. So over here, we'll get dP by dt. dP by dt is equal to delta H by RT square by P. And this P is nothing but P saturation, because Vg is actually the volume of saturated vapor. So it's going to be P saturation. So in that case, we get dP saturation upon dt is equal to delta H times P saturation upon RT square. So that is what we have. Delta H times P saturation upon RT square is equal to dt. dTs by dt. All right. So I'll write that down over here. dP S by dt is equal to delta H into P saturation upon RT square. Now I'm taking this P saturation to the denominator. So we'll get dP saturation by P saturation into 1 by dt is equal to delta H by RT square. All right. So this can be written as ln, d ln P saturation. All right. That's how we get this one. D ln P saturation by dt is equal to delta H by RT square. All right. Now, since we have also assumed that delta H is constant with respect to temperature, so we can integrate this. All right, we'll take this temperature over there and then we'll integrate from T1 to T2. And this we are going to integrate from P1S to P2S, right? So this is going to be ln P2S by P1S is equal to delta H by R. 1 upon T square has its integral as minus 1 upon T. So this is going to be minus 1 upon T2 minus 1 upon T1. So that gives us ln P2 saturation by P1 saturation is equal to delta H by R 1 upon T1 minus 1 upon T2. This is a very, very important equation, the Clausius-Clapeyron equation. All right, Clausius-Clapeyron equation has a variety of applications in thermodynamics. All right, so in case you need to predict the vapor pressure of a particular substance at a different temperature, When you're given the vapor pressure of a substance at a particular temperature, and you also know the enthalpy of vaporization, then you can easily predict the vapor pressure, right? Similarly, it can also be used for predicting the enthalpy of vaporization for a particular substance in a given temperature range, when we assume that the enthalpy of vaporization is going to be constant in that particular temperature range. Okay, now with that, we'll move on to link problem 1 and 2. All right, this problem came in GATE 2003. So 1 kilogram of saturated steam at 373 Kelvin and 1.01325 bar is contained in rigid walled vessel. It has volume of 1.673 meter cube. It is cooled to 371 Kelvin. The saturation pressure, it is reduced to 0.943 bar. In that case, the water vapor, which 1 kg of water vapor occupies 1.789 meter cube. So basically these two, 1.673 and 1.789, are basically specific volumes. These are the specific volumes given at this particular temperature and this pressure. All right. So Vg at 373 and 1.01325 is 1.673 meter cube per kg, and Vg at 371 and 0.943 bar is equal to 1.789 meter cube. All right. Then we have also given that 1 kg of saturated steam is contained in a rigid walled vessel. So that means that the volume of the rigid walled vessel, which contains 1 kg of steam at 373 Kelvin and 1.01325 bar, the volume of this vessel is equal to the specific volume at this particular at these conditions. The reason being that it is only 1 kg, so it's going to be equal to the specific volume. So that is 1.673. The volume of the vessel is equal to 1.673 meter cube. All right. Now let's solve the first part of the problem, or the first problem, the amount of water vapor condensed. Now, keep this in mind that since the temperature is quite close to 100 degrees Celsius, so we are going to assume the liquid density, that is density of water is equal to 1000 kg per meter cube. All right, we are going to assume this. Okay, so keep this in mind that when density of liquid water is not given, we assume it as 1000 kg per meter cube, since there is no data available. So in that case, volume in the liquid phase is given to be 1 upon density. Specific volume in the liquid phase is 1 upon density, specific volume of saturated liquid. So that is going to be 1 upon 1000. That is 10 to the power minus 3 meter cube per kg. This is my specific volume of saturated liquid. Okay. Now, once you have specific volume of saturated liquid, then you know that the temperature, when it is reduced to 371 Kelvin, and temperature is reduced to 371 Kelvin, and pressure is reduced to 0.943 bar. So in that case, the volume is definitely going to be the volume in the liquid, volume of vapor, since it is 1.789. Specific volume of vapor is 1.789 meter cube per kg, and the specific volume of liquid is 10 to the power minus 3 meter cube per kg. But the total volume that is occupied by this mixture is equal to the volume of the tank. That cannot be changed. That means since this volume is between gas and liquid volume, therefore we are going to assume that it's going to be somewhere here, right? So when it is a partially condensed steam, then something called quality comes into picture. We have studied this, quality, right? So X comes into picture. So in that case, we are going to have the specific volume of this mixture is equal to Vg into quality plus 1 minus x into VL, right? We have these things. V is going to be 1.673. That is what is desired. Vg is 1.789 given in the problem. All right. And 1 minus x into VL is 10 to the power minus 3 based on the assumption taken by us. All right. So from here, x comes as 0.935. Now, if you remember, 0.935 or x is basically the quality, which is dryness fraction. So this is mass of steam upon total mass, right? Mass of steam upon total mass. Total mass is going to be the same, that is 1 kg. So this is basically your mass of steam. Therefore, mass of water, that is 1 minus x, that is going to be 1 minus 0.935, which is 0.065 kg. All right. So B part is the correct answer. All right. Then we have to calculate the latent heat of condensation in kilojoule per kg under these conditions. So remember, for latent heat of condensation, we have to use the Clausius-Clapeyron equation, right? Whenever condensation or evaporation comes into picture, then we use Clausius-Clapeyron equation. So by Clausius-Clapeyron equation, we have ln P2 saturation upon P1 saturation is equal to delta H by R 1 upon T1 minus 1 upon T2. All right. So now T1 is 373 Kelvin. T2 is 371 Kelvin. P1 saturation is 1.01325 bar and P2 saturation is 0.943 bar. All right. R, we are going to take whatever we want for our. So R we will take as 8.314 kilojoule per kilomole Kelvin. So from this, when we'll get delta X, that would be in kilojoule per kilomole Kelvin. All right. So on substituting everything, we get delta H, which is 4133.4374 kilojoule per kilomole. Now, what most students will do, they'll go to the options and they'll see that A option is very close to this. So they'll put this as the correct option. But that's not the case. Because what we have found is basically latent heat of condensation in kilojoule per kilomole. What is required is the latent heat in kilojoules per kg. So keep in mind about the units that you're solving. All right. So we have to convert this kilomole into kg. So we are talking about water. So molecular weight is 18. So we'll divide by 18 kg per kilomole. So we'll get everything in kilojoule per kg. So this comes out to be around 2296 kilojoule per kg. Now if we go back, so this option is closest. So 2676 is our answer. All right. Hope you're clear with how to solve problems like this.